All right, welcome back to Rad on Smart Review. Today, we're jumping straight into a core concept in radiation biology.
Yeah, how we model cell survival after radiation. It's fundamental.
Exactly. We're going to tackle target theory and the linear-quadratic model, the LQ model.
Right. And these aren't just, theoretical exercises. They underpin how we plan treatments.
They really do. Understanding them helps predict how cells respond, both the cancer cells and the normal ones.
Absolutely. So maybe let's start at the beginning. How do we even get the data for these models? Like, how do radiobiologists measure survival?
Good starting point. The workhorse method is the clonogenic assay. You've probably heard of it.
The colony-forming assay.
Right. Basically, you take a dish of cells, you irradiate them, spread them out really thin.
So they're individuals.
Yeah, and then you wait. You see which cells can still divide and form a little clump, a colony.
And each colony, ideally, comes from one single cell that survived the radiation.
Precisely. So you count those colonies after different radiation doses, and that lets you calculate the fraction of cells that survived.
Okay, and then you plot that data. Surviving fraction versus dose.
Yep. Usually the surviving fraction is on a log scale, and the dose is linear.
And for the kind of radiation we use clinically, low LET photons, what does that curve typically look like?
You get that very characteristic shape. There's an initial sort of flat part or less steep part, the shoulder.
Right, at low doses.
And then as the dose goes up, the curve gets steeper and looks more like a straight line on that semi-log plot.
That shoulder is really the key feature, isn't it? It tells you something important is happening at lower doses.
It does. And that's what these models, target theory and LQ, try to explain. Why the shoulder? What does it mean biologically?
Exactly. They're trying to connect the physics of radiation hitting the cell with the biological outcome survival.
And like you said, this isn't just academic curiosity. It has huge implications for treatment planning for fractionation.
Definitely. Okay, so let's rewind a bit. Talk about target theory, one of the earliest ideas.
Yeah, where did that come from?
Well, a lot of the early foundational work was by Puck and Marcus back in the 50s using HeLa cells.
Okay.
And the basic idea is kind of intuitive. Radiation causes damage by delivering hits to critical targets inside the cell.
Like little bullseyes. Hit the bullseye, cell dies.
Sort of, yeah. At the time, they didn't definitively know it was DNA, but the concept was these critical targets.
We now know it's primarily nuclear DNA, right? That's the main part.
Overwhelmingly, yes. So the simplest version within target theory is the single target, single hit model.
Okay, break that down.
It assumes there's just one critical target in the cell.
One bullseye.
One bullseye. And just one hit on that target is enough to inactivate the cell. Game over.
And what kind of survival curve does that predict?
That predicts a purely exponential curve.
No.
A straight line right from the origin on the log linear plot. No shoulder.
Okay. And there's a formula for that.
Yep. S equals E to the minus D over D0. S is survival. E is, the natural log base. D's in dose.
And B0.
D0 is a constant. It reflects the target's sensitivity. A lower D0 means the cells are more sensitive, the slope is steeper. Higher D0, more resistant.
But that simple model doesn't really fit the shouldered curves we usually see with photons.
Correct. It works well for some situations, which we'll get to, but not for typical low LET radiation. So target theory needed an upgrade.
Which led to?
The multi-target single-hit model.
Okay, multi-target, so more than one bullseye now.
Exactly. The idea here is that there are multiple targets, let's say N targets.
N target.
And each of those N targets needs to get hit at least once for the cell to die. All N must be inactivated.
Ah, okay. That sounds like it could explain a shoulder. You need to accumulate enough hits across all targets.
Precisely. It allows for some initial damage to be absorbed before lethal inactivation occurs, and this model can generate that shouldered curve.
Does it have a formula too?
It does. It's a bit more complex. S equals 1 minus, then in parentheses, 1 minus E to the minus D over D0, all raised to the power of N.
Okay, so we still have D0, but now we also have N, the number of targets.
Right. And these parameters tell us about the curve shape. D0 is still related to sensitivity, specifically on the final straight line part of the curve at high doses.
How is it defined in this model?
It's the dose needed to reduce survival down to 37% on that final exponential slope. It represents the dose required for an average of one lethal hit per target in that high-dose region.
And that 37%, that's Poisson statistics again, isn't it?
Exactly. It comes from E to the minus 1. At a dose D0 on that final slope, the probability of a target not being hit is E1, or about 37%. So 37% survive due to having 0 hits on a specific target, assuming Poisson.
Got it. And The number of targets. But what does that tell us visually on the graph?
So n is called the extrapolation number. If you take that final straight part of the curve and draw it back, extrapolate it to the e-axis zero dose, the value where it intersects is n. So theoretically, it's the number of targets, but practically, it's really a measure of the shoulder width. A large N means a broad shoulder.
Suggesting more capacity to accumulate sublethal damage? Or maybe more efficient repair?
Kind of, yeah. It reflects the cell's ability to withstand initial hits. If N equals 1, you're back to the single hit model, no shoulder at all.
And there's another term, DQ, quasi-threshold dose.
Right, DQ. It's another way to measure the shoulder. It's the dose where that extrapolated straight line crosses the 100% survival level or survival fraction of 1.
How does it relate to N in D0?
There's a formula. The natural log of N, ln equals DQ divided by D0. So bigger DQ also means a wider shoulder.
Okay, so target theory gave us D0N and DQ to describe these curves. You mentioned that sometimes we do see exponential survival where N1. When did that happen?
Good question. Target theory helps us predict those situations. A major one is high LET radiation.
Like alpha particles, neutrons.
Exactly. These deposit energy very densely. Think of them causing complex, non-repairable damage clustered together. One track might be enough to kill the cell directly.
So they bypass the need for multiple hits, like a cannonball versus shotgun pellets.
Great analogy. The dense ionization track acts like that cannonball, causing overwhelming damage in one go. It essentially removes the shoulder.
What else leads to exponential survival?
Well, cell cycle position matters. Cells in M phase, or G2, are generally more sensitive and show less of a shoulder.
Less time or capacity for repair in those phases.
That's the thinking. Also, some cell types are just intrinsically very radiosensitive, like hematopoietic stem cells. They often have nearly exponential curves.
And what about repair itself?
Ah, yes. Cells with defective DNA repair mechanisms, especially for double-strand breaks, can't handle sublethal damage well. They'll show a much steeper curve, often with little or no shoulder, closer to exponential.
Okay, so target theory was a really important step, but you said the linear-quadratic, or LQ model, is more favored today, especially clinically. Why the transition?
Target theory was great conceptually, but the LQ model seems to fit the experimental data better, especially in the dose ranges we use per fraction in the clinic, say 1 to 5 gray.
It's a better match at lower doses.
Generally, yes. And it also links more directly to potential biological mechanisms of damage and repair. It's become the standard framework for understanding fractionation effects in tissues.
So what's the core idea behind the LQ model? How does it explain cell killing?
The LQ model assumes that cell killing comes from two main components of damage, both related to DNA lesions.
Okay, two components.
One component is proportional to the dose itself, just D, that's the linear part. The other component is proportional to the square of the dose, D squared, that's the quadratic part.
And the survival formula reflects that.
Exactly. Survival S equals E raised to the power of negative alpha D minus beta D squared. So S, E plus BD.
Let's unpack alpha and beta. What does alpha represent?
Alpha is the coefficient for that linear component. It represents the probability of cell killing from a single radiation event, causing lethal, non-repairable damage.
Like maybe one track causing two very close DNA breaks. A complex lesion.
That's a common interpretation, yes. Damage that the cell just can't fix effectively. This alpha component dominates the cell killing at very low doses and sets the initial slope of the curve.
Okay, and beta, the quadratic part.
Beta is the coefficient for the D squared term. It represents cell killing that results from the interaction of two separate, independent, sublethal damage events.
So like two different radiation tracks causing breaks that then combine.
Precisely. Imagine two single-strand breaks, maybe from different tracks, happening close enough in space and time that they interact to form a lethal double-strand break. This type of damage is considered potentially repairable.
And because it depends on two events, its probability increases with the square of the dose.
Exactly. That's why it's the EBD term. This component becomes more important as the dose increases, causing the survival curve to continuously bend downwards on the semi-log plot.
So unlike the multi-target model, which predicts a final straight slope, the LQ curve is always bending.
Technically, yes, it's continuously bending, though at very high doses, the beta term dominates so much that it might look almost straight again, but mathematically, it's always curving.
Now, you mentioned this model is key for fractionation. A really critical concept comes out of this, the alpha-beta ratio.
Ah, yes, the output ratio, incredibly important clinically.
How do we calculate it, and what does it tell us?
Calculation is simple. It's just alpha divided by beta. The units are dose, usually gray.
Okay.
What it represents biologically is the dose at which the contribution to cell killing from the linear component, APR-D, is equal to the contribution from the quadratic component.
The dose where the two killing mechanisms are contributing equally.
Exactly. And this ratio is a powerful indicator of how sensitive a tissue or tumor is to changes in the dose per fraction.
How does that work? What does a high or low ratio mean?
Okay, so tissues with a high R ratio, typically around 10 gray or sometimes even higher.
Like many tumors and acutely responding tissues. Skin, gut lining.
Correct. For these, the linear alpha component dominates cell killing over a wide range of clinical fraction sizes. The survival curve is straighter. This means they are less sensitive to changes in fraction size.
Less sensitive to fraction size. Okay.
Now, tissues with a low OT ratio, maybe around 2 or 3 gray.
Like late responding normal tissues. Spinal cord, lung, kidney.
Exactly, those. For them, the quadratic beta component becomes significant much earlier, even at lower doses per fraction. Their survival curve bends more sharply, meaning they are very sensitive to changes in fraction size. Using larger fractions causes a disproportionately large increase in damage compared to tissues with a high OT ratio.
Okay, so that's the radiobiological basis for fractionation sparing late effects.
Precisely. Giving the radiation dose in smaller fractions exploits this difference.
How so?
By giving smaller doses per fraction, you reduce the impact of that beta component, which is more significant in the late responding normal tissues, low OT. It allows those tissues more opportunity to repair the sublethal damage between fractions.
Because the shoulder, whether you think targets or beta damage, represents repair capacity.
Exactly. Tumors and acute tissues, high Luke, are less affected by the change to smaller fractions, relatively speaking, because their damage is more alpha-driven anyway. So fractionation gives a therapeutic advantage.
It differentially spares the tissues we're most worried about for long-term side effects.
That's the key idea. And the LQ model, specifically the AC ratio, provides the quantitative framework to understand and predict this. It helps us compare different fractionation schedules.
Like hyperfractionation smaller doses more often.
Right, designed to further spare late tissues.
Or hypofractionation larger doses, fewer treatments.
Which might be suitable if the tumor has a high AC or if the tumor's AC is significantly lower than the surrounding tissue, though that's less common. It's all about exploiting those AC differences.
Okay, this is really tying things together. Let's pause for some clinical pearls. What are the absolute take-homes here?
Okay, pearl number 1. That shoulder on the survival curve, it represents repair. Whether you use target theory or LQ, it signifies the cell's ability to fix sublethal damage. More shoulder, more repair capacity.
Got it. Shoulder equals repair. Pearl 2.
Pearl number 2. High LET radiation is different. It mostly bypasses that shoulder effect because it causes dense, often irreparable damage, leads to more linear, exponential-like killing. Fractionation doesn't offer the same sparing benefit with high LET.
Okay, high LET. Less repair, less shoulder. Final pearl.
Clinical pearl number 3. The LQ model is our workhorse clinically. It fits the data well at typical fraction sizes, and crucially, the ALA ratio derived from it helps us understand and predict tissue responses to different fractionation schedules. Master the LQ model and the OC concept.
Excellent pearls. Now let's pivot slightly to clinical decision-making. How does this IA ratio practically guide us when we're planning treatment?
It's central. As we said, high-OT tissues, like tumors and acute responding tissues, around 10G, are less sensitive to fraction size changes.
Meaning you have more flexibility.
Sort of. It means that compared to low-OT tissues, the biological effect doesn't jump up quite as dramatically if you increase the fraction size moderately. This opens the door sometimes for hypofractionation.
Fewer, larger treatments.
Right. Conversely, low-OT tissues, the late responding ones like spinal cord, lung, kidney, around 2-3G, are highly sensitive to fraction size.
Because that beta D squared term kicks in harder for them.
Exactly. So even a small increase in dose per fraction can lead to a big increase in late toxicity risk. That's why we're generally very cautious with fraction size near these critical organs. We tend to prefer smaller fractions.
Okay, let's run through a scenario, say prostate cancer. Generally considered to have a low OT ratio, maybe 1.5 to 3G. People are using hypofractionation more now. What's the thinking?
Great example. If the tumor's OT is truly low, maybe even lower than some surrounding late tissues like the rectum.
Which also has a low OT.
Right. Then using moderately larger fractions could potentially increase the biological dose to the tumor more effectively than it increases the dose to the rectum, relatively speaking. Or at least you might achieve a similar biological effect with fewer treatments, which is convenient.
But it's a fine line because
Yeah.
both have low OT ratios.
It's a very fine line. It relies on that potential difference in OC, however small, and crucially, on highly conformal dose delivery IMRT image guidance to minimize the dose to the rectum and bladder. The potential benefit is shorter treatment, maybe better biological effect, but the risk is increased late toxicity if not done carefully.
Okay, different scenario. Head and neck cancer, often treated at high doses near the spinal cord. Tumor os is probably high, maybe 10 chi. Cord is low, maybe 2 chis. How does fractionation play out?
Here, the difference is huge. The spinal cord, low A, is exquisitely sensitive to fraction size. The tumor, high O, is much less so.
So you definitely don't want large fractions hitting the cord.
Absolutely not. This is the classic situation where standard fractionation, like 1.8 or 2 Grij per fraction, is strongly favored. It protects the cord by keeping the dose per fraction low, minimizing that beta effect in the cord.
While still delivering a high total dose to kill the tumor, which responds well even to smaller fractions because of its high alpha component.
Precisely. You might even consider hyperfractionation even smaller doses, like 1.2 Gauge twice a day, to push that differential sparing of the cord even further, though that's less common now with IMRT.
It really shows how understanding odd dictates the strategy. And this links into treatment techniques, doesn't it?
Absolutely. Techniques like IMRT, VMAT, SBRT, they're all about shaping the dose.
Letting us put high dose where we want it and keep it low where we don't.
Right. And knowing the OB ratios tells us how critical that dose shaping is for specific normal tissues, especially when using fractionated treatments or even SBRT near sensitive structures. Reducing the volume of low op tissue, getting a high dose per fraction, is paramount.
The radiobiology drives the need for the technology?
You could say that. The principles underpin why we develop and use these advanced techniques.
Okay, I think it's time for a quick board blitz. Ready?
Let's do it.
Question 1. In the LQ model, what does the beta component primarily represent biologically?
Beta represents cell killing from the interaction of two separate, potentially repairable sublethal lesions.
Correct. Question 2. In target theory, what does a large N value, the extrapolation number, indicate about the cells?
A large N means a wide shoulder, indicating a significant capacity for accumulating sublethal damage before dying. Suggests good repair.
Nicely put. Question 3. What kind of radiation typically shows a survival curve with little or no shoulder?
That would be high LET radiation.
ILET. Perfect.
Yeah.
And question 4. Tissues with a low alpha-beta ratio are generally most sensitive to changes in what treatment parameter?
Dose per fraction. Definitely dose per fraction.
Excellent. 4 for 4. Now, are these models settled science or are there controversies and advances?
Oh, definitely ongoing discussion. A big one is the LQ model at very high doses per fraction.
Like in SBRT or SRS, doses of 10, 15, 20 gray or more in one shot.
Exactly. Does the LQ model still hold up there? Some evidence suggests maybe not perfectly. At those high doses, the predicted cell kill from LQ might underestimate what's seen, or perhaps other biological effects kick in strongly.
Like what?
Things like damage to the tumor vasculature, or maybe a complex clustered DNA damage that doesn't fit the simple alpha-beta assumptions. There's debate about whether we need modified LQ models or entirely different models for the SBRT dose range.
So the jury's still out on ultra-high doses. What about improving the model's parameters?
That's a huge area of research, trying to get better, more specific alpha and beta values, and thus out ratios for individual tumor types, subtypes, and different normal tissues.
More personalized radiobiology.
That's the goal. If we have more accurate UF values, we can use the LQ model, or whatever model proves best, to really tailor fractionation schedules for individual patients, maximizing cure and minimizing side effects. It involves lab work, clinical trial analysis, modeling. It's complex but vital.
So these models are powerful tools, but still evolving. Okay, let's try to summarize the key points from today.
Sounds good. We started with cell survival curves, how they're measured using clonogenic assays, and that characteristic shoulder shape for low LET radiation.
Then we dug into target theory, the idea of hits and targets. Single hit giving exponential survival. Multi-target explaining the shoulder with parameters D0, N, and DQ.
Right. Then we shifted to the currently dominant LQ model. Survival depends on alpha times dose plus beta times dose squared. Alpha representing linear, single-hit killing, beta representing quadratic killing from interacting sublethal lesions.
And the crucial takeaway from LQ is the alpha-beta ratio. High OC means less sensitivity to fraction size, typical of tumors and acute tissues. Low OFF means high sensitivity to fraction size, typical of late-responding normal tissues.
And that difference is what we exploit with fractionation to improve the therapeutic ratio. Understanding OB is key to choosing appropriate schedules and appreciating why techniques like IMRT are so valuable.
We also touched on the limitations, especially at SBRT doses, and the ongoing work to refine these models.
A lot packed in there, but really core stuff for radiation oncology.
Absolutely essential. Well, that wraps up our deep dive on modeling survival.
Hope this helped clarify target theory and the LQ model for you.
For more practice, head over to radonsmartlearn.com. Check out the questions there. And be sure to subscribe to Radon Smart Review for our next deep dive.
Thanks for tuning in.